Hello everyone, my name is Alexos Zeikis, and today I will be presenting pre-trained embeddings for entity resolution and experimental analysis. This is a work done in collaboration with George Papadakis, Dimitrios Koutas, and Manolis Koubarakis. This is the outline of our presentation. We're going to start with a short introduction of the problem. Then we're going to present the evaluated language models. And then for each task, we're going to show a task definition, the datasets involved, and finally, their performance on both effectiveness and efficiency. And finally, we're going to end our presentation with our conclusions. Entity resolution is the task of detecting different entity profiles that refer to the same real-world entity. It is typically performed in two main steps: blocking, which identifies candidate pairs that are likely to match, and matching, which decides whether a given pair constitutes a match. Traditional approaches are based on high-dimensional sparse vectors like back-of-words or DFIDF vectors. These approaches capture syntactic but not semantic similarity. Language models, on the other hand, capture semantic similarity, but there is a lack of systematic analysis and comparison on various issues, such as vectorization overhead, efficiency and effectiveness of blocking and matching, impact on of fine-tuning, and performance of end-to-end pipelines. Now, moving on to evaluated language models. We have compared three categories of language models, which are presented in chronological order. The first includes static models, where each word has a fixed vector, which is agnostic to context. The first model is Word2Vec, a shallow two-layer neural network with local context window, either continuous back-of-word, order-agnostic, or continuous skipgram, order-aware. The latter ignores corpus statistics. Next is GloVe, which combines global co-occurrence counts with a local context window. And finally, we have FastText, which is based on the skipgraph model. To fix missing misspellings or mispronunciations, it splits each word into n-grams and vectorizes n-grams instead of words. Thus, each word is the sum of the underlying n-grams. The next family is the BERT models, which offer both token and sentence embeddings via the use of CLS token that capture context. The first model is BERT, which uses multiple transformers, only the encoder part, on two tasks, masked language modeling and next sentence prediction. Next, we have Albert, a lighter version of BERT, where only one encoder is trained instead of all 12, and it also reduces the number of embedding layers. Roberta is a more robust version of BERT, which is trained on more data, removes the NSP task, and changes the masked tokens per epoch. Distilbert uses distillation to produce a lighter version by using the original BERT as teacher. And finally, we have XLNet that solves a slightly different task called permutation language modeling, PLM. The third category is sentence BERT models, which produce more effective sentence embeddings efficiently via their Siamese architecture. The first model is SMPNet, which tries to solve the same permutation problem of XLNet. Note here that for SMPNet, as for other models in this category as well, we explain MPNet, which is the base model that is used in collaboration with the Siamese architecture. Next, we have SGTR-T5. T5 is an encoder-decoder model used for all NLP tasks and not just MLM or NSP. SDStill-Roberta produces a lighter model of Roberta via distillation. And finally, we have SMINI-LM, which produces a lighter model than BERT via distillation, but it does not mimic the whole network, but only the attention layers. Now moving on to the tasks. The first task is blocking, and as we have mentioned, in blocking we want to identify pairs that are likely to match. To do so, we use one of the two datasets as index. For each entity in the other dataset, we perform nearest neighbor search, NNS, and consider the k nearest neighbors as candidates. For datasets with a relatively small size, we perform exact NNS. For datasets with a relatively large size, we perform approximate NNS via the hierarchical navigable small world index. For comparison with state-of-the-art, we use DeepLocker, which uses an autoencoder with fast text embeddings. In general, for our experiments, we use datasets that are widely used in other works of entity resolution. In blocking, we use 10 real-world datasets containing descriptions of restaurants, products, movies, etc. They correspond to the clean ER task, record leakage, where no duplicates exist within each dataset, and each entity can have only one match. The first two rows show the names of the datasets, which also hint to the type of data, for example, restaurant reviews, descriptions of products, etc. The next two pairs of lines show the number of entities and number of attributes per dataset accordingly. And finally, we have the number of duplicates and the average length of a sentence inside the dataset. For blocking scalability, we use sovereign artificial datasets by extracting real names and addresses from real census data. They correspond to the DER task, application. In this table, we have only one dataset per case. Each row corresponds to the same statistics as before, meaning number of entities, attributes, duplicates, and average sentence length. First, we show the effectiveness of blocking, with plots showing blocking recall with KNN search for k equals 10. The sentence BERT-based models, especially SGTRT5, perform very well. BERT-based models, especially ExcelNet and Albert, perform poorly, even worse than static. This is something expected since they are not fine-tuned for this task yet. Compared to the blocker, SGTRT5 achieves about a 15% higher recall on average, despite its lack of fine-tuning. In efficiency, in language model comparison, all execution times are very low, and there are no big differences between methods. Thus, any plot is omitted. Any differences occur mostly when dimensions vary, meaning when we have 300 or 768 dimensions. In synthetic datasets, from the first dataset with 10,000 entities to the last dataset with 2 million entities, Word2Vec and SGTRT5 were 742 times and 873 times lower. All other models were 1,244 times on average lower. In comparison with state-of-the-art, DBlocker has similar performance with SGTRT5 for datasets D1 through D8. In D9 and D10, SGTRT5 is 4 times faster on average and up to 9 times faster. This difference is larger for large K since SGTRT5 performance does not change, whereas DBlocker has poorer performance for larger K. Finally, for summarizing the task of blocking, we show a plot with a trade-off between effectiveness on the x-axis and efficiency on the y-axis. The times in the y-axis are normalized over the fastest model. It is clear that the SBERT models clearly outperform all others in both effectiveness and efficiency. Moving on to the unsupervised matching. To do so, we want to model it as a clustering problem. We apply unique mapping clustering, which is a state-of-the-art bipartite graph matching algorithm, and works as follows. First, we weigh all edges of bipartite graph and insert them into priority queue. Iteratively, we export the next best edge. If both entities are marked as unmatched, then we mark them as matched. The algorithm ends when all entities are matched or edge weights drop below a specified threshold delta. Starting from delta equals 0.95, we decrease it by a step of 0.05, and at each step, we report the performance of the algorithm. For comparison with the state-of-the-art, we used ZeroER, which uses a generative model based on Gaussian mixture models and tries to find feature vectors for each pair from unlabeled data. It also requires aligned schemata. In the task of unsupervised matching, we use the 10 clean linear datasets as in the task of blocking. For effectiveness of unsupervised matching, our plots show maximum F1 score per case. To be noted, the algorithm is iterative, thus recall is increased at each step, while precision decreases and F1 score is maximized at different steps. Again, the sentence-based models, especially SGTRT5, perform very well, and the BERT-based models perform poorly, even worse than static. Compared to ZeroER, SGTRT5 is clearly better. ZeroER even fails to terminate in most cases, and to be noted, SGTRT5 in this case is an end-to-end pipeline using both blocking with k equals 10 and unsupervised matching. In language model comparison, the results are similar in all datasets. Indicatively, we show the results for dataset DIN10. Sentence BERT and static models have very good execution times, while BERT models need more time. That is explained on how discriminative the embeddings are. Since the algorithm has a termination condition, i.e. when all entities are matched, the BERT models need more time to match all entities and they reach lower thresholds. In comparison with state-of-the-art, ZeroER needs a lot more time to execute, and in most occasions, it fails to finish within 6 hours. Notice that the last column on the table is in milliseconds. Finally, for summarizing the task of unsupervised matching, we show a plot with a trade-off between effectiveness on the x-axis and efficiency on the y-axis. Again, it is clear that the SBERT models clearly outperform all others in both effectiveness and efficiency. Now, We investigate the supervised matching, a final task, which is modeled as a binary classification problem. For static methods, we use DeepMatcher, which takes a static model and feeds its output into a neural network, which is then trained for the entity matching task. For the existing implementation, Word2Vec was not supported. For dynamic models, we used EM Transformer, which takes a BERT-like model, the encoder part, and fine-tunes it for the entity matching task by adding an extra layer at the end for the classification. SGT-RT5 is not supported since it is encoder-decoder. For comparison with state-of-the-art, we use two algorithms. First, we use Ditto, which takes a BERT-like model and fine-tunes it for the entity matching, like EM Transformer, but also applies three extra optimizations: injection of domain knowledge, data augmentation, and summarization. The second model was DeepMatcher Plus, which trains a model for entity matching as in DeepMatcher, but requires fewer data through transfer and active learning. For supervised matching, we used 5 mostly artificial datasets overlapping with the 10 clean linear datasets. The first two columns are the names of the datasets. The third column shows how many pairs are in total, while the fourth one how many were used for testing. More specifically, they were split into 3 parts: 60% for testing and 20% for validation and testing accordingly. Moreover, the fifth column shows how many pairs are marked as duplicates, or else how many are marked as class 1, and finally, the sixth column marks how many attributes each entity has. Our plots measure effectiveness with the FA1 score. The BERT models are clearly improved in comparison with when not fine-tuned. Best model now is Roberta. The sentence BERT models are still very good, but their performance was high in the first place. Best model now is SMPNet, losing slightly to Roberta. The static models underperform the dynamic ones. Ditto, when studying state-of-the-art, Ditto shows a higher F1 of 1% higher on average than Roberta, and DeepMatcher Plus performs better than static models, but clearly worse than dynamic. In efficiency, first we see the execution times for both training and testing for all models and datasets. In general, the dynamic models are very efficient, and especially the distilled and lighter models, which need less time to train and test. Finally, for summarizing the task of supervised matching, we show a plot with a trade-off between effectiveness and efficiency. In supervised matching, BERT models are quite competitive with the SBERT ones, and the selection is up to the user and whether she values more effectiveness or efficiency. Now, let's move on to the vectorization. Vectorization is also known as serialization in literature. Given an entity profile, we convert it into a dense vector representation. We use a schema-agnostic strategy, meaning that all fields are concatenated into a single sentence. Most models offer sentence embeddings by default. For those that offer word embeddings, which are Word2Vec and Glove, we take the average of the individual word embeddings. For this task, we have used the clean linear and the synthetic datasets. And now, studying the efficiency performance, the static models have higher overhead for loading in memory, but they are fast to vectorize. Thus, they do not pay off when we want to vectorize small datasets. This does not seem to be a problem for larger datasets, though, like D9 or D10 in clean linear datasets, or the synthetic ones. On the other hand, dynamic models are fast to load and to vectorize in most cases. Now, in our conclusions, we saw the 3 summary plots that were shown before. They show the trade-off between effectiveness and efficiency. In blocking and unsupervised matching, the SBERT models clearly outperform all others, so the choice here is clear on which models to use. In supervised matching, BERT models are quite competitive with SBERT ones, and the selection is up to the user and whether she values more effectiveness or efficiency. Thank you for your attention.